Welcome everyone. Today we will discuss why a vehicle does not accelerate in the same way at all speeds. We will also understand two distinct acceleration regimes. The first is the traction limited region, which occurs at low speeds, where acceleration is restricted by tire grip on the road. The second is the power limited region, which occurs at higher speeds, where acceleration is controlled by the available motor power. These two regimes depend on how fast the vehicle is moving, and together they explain the complete acceleration behavior of a car. At low speeds, acceleration is limited by tire grip on the road. This is called the traction limited region. In this case, the maximum tractive force is given by Fmax equals mu times mass times g, and the corresponding acceleration becomes A equals mu times g. At higher speeds, the limitation changes. Acceleration is no longer controlled by traction. Instead, it is controlled by how much motor power is available. This is called the power limited region. In this region, tractive force is defined by F equals P divided by V, where P is motor power and V is vehicle speed. The resulting acceleration is A equals P divided by M times V. This shows that acceleration decreases as speed increases. So in summary, at low speed, acceleration depends on road grip. At high speed, acceleration depends on motor power. Understanding these two regimes explains why vehicles launch strongly from rest but gradually lose acceleration as speed increases. At low vehicle speeds between 0 and 30 kilometers per hour, electric vehicles operate in what is called the traction limited region. In this region, the vehicle cannot use all of its motor power because the tires can only grip the road up to a certain limit. The maximum force the tires can provide is given by the equation Fmax equals mu times mass times g. Because of this limit, the maximum acceleration becomes A equals mu times g. For the example electric vehicle shown here, this traction limit results in a constant maximum acceleration of approximately 8.83 meters per second squared. This means acceleration depends only on road grip and tire quality, not on motor power. This traction-limited behavior dominates all low-speed launches and defines how quickly the vehicle can initially accelerate. At higher vehicle speeds, acceleration enters what is called the power-limited region. In this region, the motor has already reached its maximum power output, which is described by the equation P equals F times V. As speed increases, power remains constant. Because of this, tractive force becomes F equals P divided by V. This means tractive force decreases as speed increases. The resulting acceleration is given by A equals P divided by M times V. This equation shows that acceleration drops continuously as speed rises. This behavior is commonly observed during highway driving, where vehicles accelerate more slowly at higher speeds. Unlike low-speed operation, where acceleration is limited by tire grip, high-speed acceleration is limited by available motor power. So, the limiting factor shifts from road traction to motor capability as vehicle speed increases. In this example, we use the same electric vehicle to study acceleration at different speeds. The vehicle mass M is 1,500 kilograms. The tire road friction coefficient, Mu, is 0.9. The maximum motor power, P, is 150 kilowatts. Gravitational acceleration, G, is 9.81 meters per second squared. These values remain constant throughout the analysis. Using these fixed parameters allows us to directly compare how acceleration changes between low-speed traction-limited operation and high-speed power-limited operation. This numerical example provides a consistent reference for understanding how speed alone alters vehicle acceleration behavior. Let us now calculate the traction-limited acceleration for the electric vehicle. The acceleration in this region is given by A traction equals 8.83 meters per second squared. This acceleration applies at low speeds, typically between 0 and 30 kilometers per hour. Next, we calculate the corresponding tractive force using F equals 13,245 newtons. This force represents the maximum tractive capability of the tires. Beyond this point, wheel slip will occur. So, this traction-limited acceleration defines the strongest possible launch performance of the vehicle before tire grip becomes the limiting factor. Let us now calculate acceleration in the power-limited region. at two higher vehicle speeds. First, consider a speed of 20 meters per second, which is approximately 72 kilometers per hour. In this case, acceleration equals 5.0 meters per second squared. Next, consider a higher speed of 30 meters per second, which is approximately 108 kilometers per hour. In this case, acceleration equals 3.33 meters per second squared. These results clearly show that acceleration decreases as speed increases in the power-limited region. This behavior contrasts sharply with the traction-limited case, where acceleration remains constant. So, at high speeds, motor power becomes the dominant limitation, and vehicle acceleration gradually reduces as velocity rises. Low-speed acceleration is controlled by tire grip and remains constant. High-speed acceleration is controlled by motor power and steadily decreases. This comparison brings together all earlier results and clearly shows how the dominant limiting factor shifts from traction to power as vehicle speed increases. Most EVs use a single-speed reduction gearbox. Even though electric motors provide usable torque over a wide speed range, the reduction gear ratio is still very important. This gear ratio directly determines wheel torque, vehicle acceleration, maximum achievable speed, overall efficiency, and the load applied to the motor. So, even with a powerful electric motor, improper gearing can reduce performance or efficiency. Let us now express these relationships mathematically, so we can clearly quantify how the transmission influences vehicle behavior. Because of gear reduction, a relatively small motor torque is multiplied into a much larger wheel torque. This torque amplification at the wheels is what gives electric vehicles their strong launch performance. That is why EVs are capable of excellent low-speed acceleration, even without multi-speed transmissions. Gear ratio selection affects both traction-limited and power-limited acceleration characteristics. A high gear ratio provides excellent low-speed acceleration, but it reduces the vehicle's maximum top speed. A low gear ratio results in weaker low-speed acceleration, but allows a higher top speed. Electric vehicle manufacturers carefully tune acceleration performance using several factors: the motor torque curve, the selected gear ratio, power electronics limits, and the traction control system. Because of these design choices, two electric vehicles with similar battery capacity can show very different 0 to 100 km/h times. To summarize, net vehicle acceleration is determined by the balance of forces acting on the vehicle. These include the traction force produced at the wheels, the rolling resistance from the tires, and the aerodynamic drag from air. The difference between the driving force and these opposing forces ultimately defines how fast the vehicle accelerates. The gearbox multiplies motor torque, increasing wheel torque and improving low-speed acceleration. Acceleration profiles are different in traction-limited and power-limited regions. Gear ratio balancing is a critical trade-off between strong launch performance and achieving higher top speed. These 3 points capture the core principles behind electric vehicle acceleration behavior. So finally, we see that understanding traction-limited and power-limited acceleration regimes, along with proper gear ratio tuning, is essential for analyzing electric vehicle powertrains. These concepts explain real-world acceleration behavior and guide EV performance design. Thank you all for your patience. We will meet again in another session on electric vehicle powertrain analysis.